So we're trying to do the 7.4 lesson. Okay, so I want to give a little intro to that. We'll be doing that today, Wednesday. And we get our screen to come up. So I have an interesting idea here, is that, so we've worked before with parallel lines and a transversal. And as you'll recall, you get, if you number the angles, you see that the bottom ones correspond, right? So 1 and 1 prime, 2 and 2 prime, 3 and 3 prime, 4 and 4 prime. And there's another way to think of this as well that you might not have seen before, which is that basically you have 4 acute and 4 obtuse, and the acute equal each other and the obtuse equal each other, and the acute plus the obtuse equals 180. And so you look at it and you say, okay, well, yeah, 1 and 2 are supplementary, or 2 and 3 are supplementary. Okay, but 3 and 2 prime are also supplementary. Okay, and so looking at it in that simplified way, instead of there's all kinds of relationships, like you can say 2 is equal to 4 prime, those are alternate exterior. And you could say, and if you'd like, you could say 3 is equal to 1 prime, alternate interior. But basically, you can just say there's 4 acute, they're all the same. Now, why do we consider 2 equal 2 prime? So that's this assumption over a couple thousand years old that corresponding angles in this situation are equal. You can have a geometry that doesn't assume that, and that's happened in the last 100 years. But our geometry assumes that. There's not really a proof for it. Okay? It's one of those things that are assumed. And an old word that we used to use is postulate. It's a postulate. And so then the other idea is, well, what about 2 prime equal to 4 prime, or any of the, okay, so remember that's the vertical angles being equal. Okay, but what's new here is the idea of having 2 transversals. So if we have 2 transversals, they meet, and so instead we get a triangle. Okay, and when we get this triangle, right away you see that these form 2 triangles. Okay, so a smaller one that just goes down to the first parallel line, so in green, and then a larger one that goes down to the second parallel line. And so remember from our previous work that we're sure about the similarity because we have, so if I put it in blue here, we have, for example, the angle on the left side of the smaller triangle is a corresponding angle of the same angle in the larger triangle. And that's going to be true on the other side. So we have all 3 angles similar AAA. But given that, what other kinds of proportions can you get? And so this is what they're trying to get you to do, right? Is say, okay, if I have these sides, what kind of proportions can I get? And one of the things they're trying to get us to see is that, something you wouldn't normally think of is that when I have these 2 transversals, that BD and CE are going to be in the same proportion as, say, for example, AB and AC. Okay, so that the red to the red is equal to the green to the green. We're going to try and make an argument today about that. And one of the things we're going to do is we're going to just look at the sides. And so one way to express the proportionality is to say that AB, okay, so the left side of the small triangle, is to AD. And then you say, well, what about the right side? As AC sorry. Oh. As AC, so you got to move this up or you start hitting the controls. As AC is to AE. And you say, well, that makes sense, right? The sides of the triangles are proportion, but you can break that up. And so the insight that they want you to see is that I can divide that up into AB, and then AD is actually equal to AB plus BD. And we have AC is to AE is actually AC plus AE. And you can divide them up that way. And so once you have that, and so we're going to use a similar sort of strategy on the next page. And so on the next page, we have BD, so in green, to AB. So BD, so not to AB, that's a little too long, right? So the extension of the triangle to the initial one, and we want to compare it to, on the right-hand side, the extra part that makes the second triangle to the first side, to AC. Okay, and so, well, we go back to, we know they're similar triangles. Okay, so what do we know about the similar triangles? We know AD to AB, so the long side, we know that the long side is to the short side as the long side is to the short side. Okay, so AD, the long side, is to the short side on the left, as the long side, AE, is to the short side on the right. But we can use that same idea as that we can break it up, right? So what is AD? AD has two parts. It has AB plus BD. So it has the short side and the extension compared to the short side. And on the other side, AE can be written as AC plus CE. And you're comparing that to the short side, AC. So if you take a look at that, you say, well, I can cross multiply. It should be equal. AC times AB plus BD should equal AB times AC plus CE. So let's see what we get when we do that. And so we get AC times AB and AC times BD. And we get, and we get on the other side, we get AC times AB and AB times CE. And so, well, okay, what do we got? Well, these terms seem to be the same. So we'll cancel those out. And we'll get AC times BD equals AB times CE. So let's see what that means. Okay, so we'll go back up to our diagram and see what we're left after this multiplication. So we've got AC times BD equals AB times CE. And from that, you say, well, I can work backwards, and I can say, then they must be proportional. So I must have BD to CE must equal AB to AC, which is what I was trying to prove. Okay, and then you'll go on to your assignment for the day. We'll look at that in a separate video.